Okay, so yeah, welcome to this Meow Bark talk, and Ian Mertz from Charles University will be telling us about catalytic space.
Oh, okay, good. Yep. Thank you so much, everyone, for coming, and thanks for having me here. This is my first time in both Denmark and Sweden, so nice box ticking and whatnot going on in Europe. And yeah, I'm going to talk about the field that I've been working on for the last few years, and kind of the only things that I can think about nowadays. Sorry to the first complexity people. And it's this thing called catalytic computing, which I think is quite interesting and funky. So I'm going to start off by telling you a ghost story about lower bounds that don't actually exist. So this is the tree evaluation problem. Okay. If my handwriting is completely illegible, please tell me. I will slow down. So the context for this problem is we want to separate space and time. To separate, in particular, logarithmic space from polynomial time. And there's a bunch of different ways you can try and do this. I mean, there's p-complete problems, so you can just try and prove lower bounds on those. But sometimes it's nicer to move to more structured problems where we can have some kind of handle on what's going on. And so in 2009, Steve Cook and a few other people, Pierre Mackenzie, Mark Braverman, Dustin Ware, and Rahul Santhanam, in a completely different order than the way that I said it, introduced this problem called tree evaluation. And it is as follows. But you get a tree, and the tree is going to have some height, which for today's purposes, just think of it as something like log n. And at each of the leaves of the tree, it looks kind of like a circuit, but instead of just having single bits, we're going to get something like log n bits per entry coming in at the leaves. So not just one bit, but log n bits. And in the interior nodes, well, in a circuit, you'd have something like Boolean and or ors to combine one bit from the left, one bit from the right, and spit out a bit. Here, you're getting in a whole log n bits from the left and log n bits from the right. So what's actually going to happen at each internal node? It's going to be an entire function from log n bits on the left, log n bits on the right, mapping to log n bits. And where does this function come from? It's given as part of the input. So the entire tree evaluation input will be the leaf values and all of the functions in the interior of the tree. At which point, the function is simple. Start at the bottom and evaluate your way up to the top. You know, every node has two children and a function to tell you how to output something. So at the end, this is going to be the output of the function coming at this top node here.
Do we worry about how the functions are represented, or should we just think of them as truth tables?
Completely just a truth table, or the search version of
truth table.
Yeah. It's a lookup table. Mm-hmm. So this is given as part of the input to the function, which means that the input to tree evaluation, unfortunately, I can't do the infinite whiteboard on this thing. So n, which is the size of the input, is something like well, the size of the tree is just, oh gosh, I'm using n two ways here. All right, I'll use capital N, whatever. The size of the tree is 2 to the log n, so it's, n times the number of bits that you need at each internal node, which is a table of log n bits on the left and log n bits on the right. So that's n squared possible entries, each of which you have to specify the entire output, which is log n bits. So it's roughly like this, and then there's the leaves and whatnot, but this is the dominating factor. And for the purposes of today, this means that log capital N is something like order of log. That's fine. Now, why study this problem? First of all, it's got a polynomial time algorithm. And the polynomial time algorithm is exactly what I just said. Start at the bottom, evaluate your way up to the top. You have everything written in front of you. You can just work your way up. Now, what's the space complexity? let's think about what would be a nice, easy way to do this in a way that preserves space. Like if there's some kind of ordering in which we can compute things so that we don't have to store so much in memory. Of course, just starting from the bottom and going all the way up is linear space, but we have much more clever algorithms, especially those based on pebbling. And we're not going to go into pebbling. You can just look at this and kind of see what the right solution is. At every step in time, if I want to compute a node, I'm going to compute its left child recursively, save the value, and compute the right child recursively. This is going to be about the best thing I can do. So when I say compute the left child and then compute the right child, I mean when I'm done computing this left node over here, erase everything that I am remembering except for that value. Everything else below this is no longer relevant. I can just save that one value and move on to the right-hand side of things. This is a very nice recursive structure. And what is the total space for it? Space, let's call it tree evaluation problem of height h. Height h is equal to the max of the left and the right, which each of them are tree evaluation instances of height h minus 1. So on the left-hand side, it's just height h minus 1. On the right-hand side, it's h minus 1, but I had to remember that value from the left. I have to save that thing for later, right? So I have to, when I actually move on to this node, I do have to remember this value. And this is all the space that I need, because once I've done this and I've done this, then I just combine them together, get the output, done. And pretty easy to just, this is not the max value, so it's just this thing on the right-hand side, and thus you get space is at most log squared n. And under a number of believable conjectures, this is the best you can do. This is certainly the best order in which to evaluate the tree, if all you're doing is evaluating nodes and remembering as little as possible. This is the optimal ordering. This is where that pebbling thing I said comes in. And it doesn't seem like there's any more clever way to do it, because if you're remembering stuff in a different order, you're remembering more information. And what I said all holds, right? This really is just a tree evaluation instance of height h minus 1. Yeah?
Log n, log h, and h is log.
Yeah. So really, if I specify this as being like b bits of input and height h, you get the size of the instance is like h plus b, and this algorithm will give you h times b. So if this holds, this is the separating instance between log space and polynomial time, right? This requires quadratically more space than we would hope, while the time complexity is, even in some sense, sublinear, because at each internal node, you only have to read one entry in the truth in the function table. And there's just like, so there's a couple of things you'd have to prove in order to get this to work. You'd have to prove that the optimal algorithm really does look at values in the tree and like compute them in some order and remember them. And there's kind of a weird technical piece of this, which is that when I say that on the right-hand side, you have a height h minus 1 instance of tree evaluation, it's not like totally correct that that's all you have, because if you're looking at your memory, when I compute the left child of the root, I have some value here that I'm storing. So this is like left value 1. And then, I'm computing the left value of the next node down, the thing on the right. And so I'm remembering L2. And so I'm remembering some values. And what we're saying is that really it's like a tree evaluation height instance of height h minus 1 or h minus 2 and whatever that requires this free space. That's whatever's left over. And that this memory that you're remembering for the other values in the tree for later, that's not actually relevant, right? That's just some memory that's going to be used to do your computation later. So it's not, strictly speaking, a height h minus 1 instance. It's height h minus 1 instance where you have a little bit of extra space, but that's in use for something completely different. And this sounds like a small little technical point, and in fact, this breaks the entire thing. So what we're going to talk about today is that if you have memory that's being used to store something, that is an extremely powerful computational resource, no matter what that thing actually is. So let me just give away the punchline, by the way. So right now we have the space down to log n times log n. There's been a minor improvement, which gets log n times log n over log n. And yeah, who knows? So now to introduce catalytic space, which is a model that was devised about halfway through the lifespan of this problem to figure out what is even going on here.
So a question about the tree evaluation problem is, was there some intuition for why this would be like a good example? I mean, it's very natural, but is it like complete for some class, or does it show up in a different?
We have no notion of completeness. We don't know this thing. I mean, one thing, it's the tree version of the circuit value problem, right? So when I said at the beginning, do a p-complete problem, you've only gone one step removed from that. It's really just that if you argue about circuits in general, the search space is so huge that focusing on one architecture, but beefing up the number of bits needed at each node so that you can analyze this thing through pebbling was the most straightforward approach. And again, they got lower bounds in the first paper. So they got log squared and lower bounds, assuming some types of restrictions on your algorithm. Unfortunately, those restrictions just don't, you can do better than them. So like read once and some other natural restrictions. Yeah, this does not show that P is going to be equal to L. Could be, it'd be fun. But
so another question is, I mean, it's intuitively clear that if the functions are completely, could be anything, then it seems like the tree evaluation, the natural algorithm you said, is the natural approach. But I mean, how could you rule out that I somehow analyze the functions and then start, I don't know, computing partial values or maybe the XORs of the values in different nodes?
Sure.
Like go completely, I mean, it's not just about catalytic space, it's about like crazy bitwise operations.
So there were a lot of angles of attack. I want to emphasize that there was no reason to believe that this would be the thing that would get you the low space algorithm. You can try a lot of things. A lot of different attacks on it. And so people kind of started to almost study the strong versus weak version of the problem, like in the sense of KRW, where you assume, basically the function in some sense is like a black box that you don't have much access to and stuff like that. Turns out that none of that's going to help you because this circumvents all of those.
So in particular, the upper bound is sort of in a black box setting where I either know the full value of a node or nothing about the node.
Yeah, I mean, you end up having to query. You do end up using the whole function, so you're going to end up querying it all. But you don't need to. You can query it all in real time. Like at any point in time, I want to know the whole function for this moment now, and then I kind of later on, I'm not paying attention to this function when I'm off somewhere else. Mm-hmm. It's a bit of a weird algorithm, but we'll talk a little bit about it later. In fact, for the second half, for the technical part, we can do whichever technical parts people care about. I'm going to throw out a few instantiations of like techniques in this field, and we can go in depth on whichever one people like the most. So what is this field? So this problem of having to store extra memory and showing that it's not useful as a resource was something that came up in discussions maybe 3 or 4 years after the original paper. And so Buhrman, Cleve, Kotsky, Loff, and Spielman decided to introduce a model just to see, like, what does this used space mean? And they came up with a catalytic Turing machine. So in the classic Turing machine model, we've got an input tape, which is read-only. You have your space-bounded work tape. Think of this as like order log n bits, as it will be for most of this talk. And you have like a little output register, maybe 1 bit. Maybe it's a search problem, so maybe there's more. If there's more bits, then it matters whether, but for it's write only. So, you can't use it for memory. This is the typical setup for log space. And in the catalytic setup, you add 1 other tape, which they call the catalytic tape. And think of this as being much, much longer than the work tape, something like poly n bits, exponentially larger. If this was just given to you with unfettered access, this would be P space directly. But this space does have a restriction. Should I start using other colors? I have other colors. Let's use other colors. Okay. The catalytic tape does not start empty. The catalytic tape starts full. So the catalytic tape is initialized to some arbitrary string tau, which is completely out of your control. And the restriction is that the machine on every input x and every starting catalytic tape tau, when you run it, you output f of x, and restore tau in the catalytic tape. That's the model. What is the word catalytic? All right, catalytic, as many spam emails who have read the paper titles that I have and have informed me, catalytic is a field of chemistry wherein a reaction can't occur on its own, but in the presence of some extra, not information, some extra chemicals, it can occur. And this process preserves the chemicals exactly. So that's kind of the restriction. So a catalyst is something that allows a reaction to happen while itself being left unchanged at the end. In the interior, it is changed. It undergoes a transformation, but somehow at the end of it, that transformation is then reset or restored. And so in particular, this catalytic condition is exactly that. Is there something that we can do using this space, despite the fact that we have to reset it, regardless of what it is, that we couldn't do with just basic log space? So.
And the intuitive answer, no way, is very, very wrong.
And the intuitive answer, no way, is very, very wrong. If your intuition is better than mine, then maybe the intuitive answer is, oh yeah, of course, that's very useful. But are you kidding me? Like, come on. This thing could be anything. How could this possibly help you with your computation? How could this class, which we call catalytic log space, be any more powerful than L? How much more powerful is it than L? So just to state the obvious, catalytic log space is somewhere between L and P space, right? Even if you somehow erased your tape, you would have no more than P space. And even if you ignored your catalytic tape, you'd have something at least that's L. And what the very first paper showed, which is basically unsurpassed to this day, is that on the upper hand, you can get CL is contained in both BPP and NP. In particular, this is ZPP, zero-sided error randomized polynomial time. And conversely, catalytic log space is at least as powerful as both BPL and NL. This catalytic tape is more powerful than randomness or non-determinism, and in fact contains problems that we think of as definitely being outside of either, such as the determinant. So this is a very surprisingly powerful class. To this day, we don't know if catalytic log space is in P. If you assume ZPP equals P, which I think most people believe, then that's that. We don't know if it's even easier to show CL is in P, substantively easier to show CL is in P than ZPP is in P. We kind of have no intuition about this. And on the flip side, we haven't really strengthened past TC1, with one small exception, which I'll talk about later. And this is the state of affairs. Like, this is all we know about the resource and in the context of space-bounded computation. And the techniques to show these things are quite interesting and very different from a lot of the things that you see in typical complexity. So we're going to talk a lot about techniques later. But for starters, I say we don't know anything else, but we've now defined a model. So let's analyze it on its own terms. So I'm about to talk about what we know. Anyone have any questions before that?
What is the smallest deterministic space class that is contained?
P space. I mean, we don't have better for BPP or P or.
For NL, you do.
Oh yeah, NL is way within. NL is in deterministic space log squared n. Yeah, we don't know anything like that for CL.
Yes.
Yeah. It would be amazing to show that CL is in log squared space. Just, I guess, anecdotally. Of course, it would be far more amazing to show that log squared space is in CL, because that would separate whatever. Would that separate anything? No, but L squared is not known to be in polynomial time or ZPP. So that would be like some shocking turn of events. All right, so we're good to go. Great. No, doesn't have it. Sorry, my notes for the talk are on my tablet. Bit of a cyclic dependency issue, but we'll figure this out. All right, so I have now defined an augmentation of log space. So you can ask the question, how does catalytic space play? Catalytic space is more powerful than non-determinism and randomness. Can I say anything else about it? Sure. It's more powerful than non-determinism or randomness, even when you also have catalytic space. Oy. The non-deterministic and randomized variants of catalytic log space are equal to their deterministic variants. This is a recent turn of events that I'm not sure we expected, but it is what it is. So given access to both resources, and I should emphasize here, since a CL machine can run for potentially exponential time, we make no restrictions on how much non-determinism or randomness you're allowed. You're allowed an exponential amount if you want it. And nevertheless, this does not add any additional power to the model.
Do you also have pseudo-random generators?
That's not really how. It's not quite how the technique goes. We'll go into the technique for this one in a bit. It's a very. I don't even know how to answer that question because of a strange reason. CL has no known complete problems. Very stupid reason for this. Pick your favorite class. Its complete problem is I give you an object from that class, just output the answer to the machine, right? NC1, I give you a formula, evaluate the formula. That can be done with a formula, stuff like that. If I give you a machine and I claim it's a catalytic log space machine, and I tell you, please run this for me and tell me what the answer is. If that machine is not, in fact, a catalytic log space machine, but destroys your catalytic tape, you will find out far too late for this to actually work. So normally you say, if I don't give you a machine from the class, detect this and just output, failure or something. But since you cannot detect whether or not a machine is actually catalytic, you can't run it in catalytic log space. Now, of course, this means the corresponding promise problem is the complete problem, just for obvious reasons. If I promise you it's a catalytic machine, cross my fingers, hope to die, then there's no problems. But in the classical world sense of it, this is an issue. And speaking of, we have the space hierarchy theorem for catalytic machines. Like that. With one bit of advice. So the space hierarchy theorem goes through as long as you allow one bit of advice. What is that one bit of advice? Is it a catalytic machine? Yeah, unfortunately, we just keep running into this issue. I don't know how to get around it, but it's not a big sticking point.
Diagonalize, but when you do the simulation for the diagonal, you need this advice.
Yeah. So in particular, I think it's something like so CL1 is strictly contained in, I'm just going to call it omega CL1. And I think you can even boost this up to be like some constant number of bits advice A. There's other settings for the case where you have polynomial, the polynomial C space world, etc. It's kind of the finicky conditions that you get from a lot of these hierarchy theorems where things aren't where the models are a little bit messy. There's nothing better or worse than a lot of those. Okay, robustness. I've given you this setup where you have exponentially more catalytic space that I want exactly reverted. You can play around with the parameters and ask, what happens here. Now this one, I can't quote off the top of my head. So that's not the correct one either. Okay, that's not the correct one either. There it is. All right, you see nothing. When I write C space something comma something, I mean that the free space is the first thing, the catalytic space is the second thing. So normally, this catalytic log space is C space log poly. If you want to mess around with the parameters, you get things like that knapsack could be solved in free space poly n and catalytic space poly n and the capacities. So normally the capacities come into the space complexities for your algorithms for knapsack. Here, all of the space complexity regarding the capacities can be offloaded into the catalytic space itself, with your free space only depending on n. Kind of a nice thing. Similarly, with de-randomizing BPL. BPL, it's known how to de-randomize in log squared space. In fact, you can get better than that. You can get all the way down to 3/2. The runtime is going to be dependent on how much you want to decrease things. But the point is that in the catalytic world, you can kind of shunt all of the non-logarithmic space off into the catalytic part. So using very little catalytic space, again, maybe this goes back to your question, like intuitively, this is going to be like the catalytic space is going to serve something like the seed of the generators in question. It's going to be a stand-in for that space. You can just use the computation, the free space as your computation space and deal with all the other issues in the catalytic part. Now, in terms of robustness,
Yeah, do you expect it to become 3/2?
So I should specify you can do this in 1 plus alpha n log to the 2 minus alpha n for all alpha in 0, 1/2 inclusive. So it depends on what you're shooting for. This is a similar trade-off to what happens in the real world, where the real world. Freudian slip. Your runtime, if you want to decrease the amount of pure space that you need for BPL to log to the 2 minus alpha n, your runtime is 2 to the log to the 1 plus alpha n, something like that. So, and that holds here too. We'll talk about some averaging arguments in a bit.
Is it the Sachs and so thing?
Yeah, Sachs show there's a trade-off. There's an interpolation between them, which is like, I don't know, Van Malkbeek and someone else. Yeah. So right, this is the exact trade-off. Okay, I want to mention something about the robustness of this model, because a natural question is, how strict do I need to make this resetting condition? You know, if I'm allowed to make a bit of error on the catalytic tape, what happens? Of course, if you know where that bit of error is, then it's no problem, but the bit can occur anywhere. So does this change the model at all? So we're going to call lossy catalytic log space with E to be catalytic log space where I allow you up to E errors on your catalytic tape. E errors in a pure sense. So like, yeah, 0 would be 0, 1 would be 1 error, and poly n would be poly n errors. So not as a fraction of the catalytic tape.
So you mean when you try to restore, you mess up E bits?
Yeah, you mess up. You can mess up to E bits. In fact, instead of doing this in the log space world, I'm going to spell it up using parameters because it will be easier to state what happens. So again, C space C is S free bits of memory, C catalytic bits of memory. LC space is lossy catalytic space where I allow you to lose E bits of the original thing. I did not make up the terminology. There have been a lot of complaints about terminology in the catalytic world. Not my problem. So what is the natural inclusion on the other side? I'm going to shrink this a little bit. Okay, so clearly this thing is at least as powerful as just having, you know, the base model with no errors. But what's a natural? How much? What do you think it takes to recover those errors? The error correcting code people in the audience? Anyone? How many bits do you think it takes to recover E errors on this catalytic tape? 2 to the E on a tape of length C. Fair enough. E log C. essentially like the amount of information it takes to write down the positions of the errors. It turns out you can do an error correcting code and get that. So S plus E log C, and then C. I'm suppressing the big O's here. So this is the kind of natural things. And the question is, actually, where does this lie? Clearly, if I make a constant number of errors, the model doesn't change. So that answers the 1 bit or so number of errors. But if I allow you slightly super constant in one of these models, oh, sorry. This can do C space something more powerful. This is S plus E, C. Right, I can just erase E bits off of my catalytic tape and use them for free memory. Which means if I make a super logarithmic number of errors, in the case, the catalytic log space case, S is log, C is poly. If I make a super logarithmic number of errors, I'm getting super logarithmic space, just for obvious reasons. But if the right-hand side is closer to the truth, then even making a super constant number of errors gives me super logarithmic free space. And it turns out that that is the answer. This is an if and only S, up to a very small constant scale. So corrupting E bits on your catalytic tape is exactly equivalent to giving you E log C extra free bits of memory. And that's essentially exactly what we need to know about the robustness of the model. So yeah, again, if you don't know, since we don't know that any space greater than logarithmic is in ZPP, you can't expect any super constant number of errors to be equal to the base model. Because of just tracing it out. All right, so that's all the internal stuff about the model. And then, of course, the real question is, like, what can it do for me? Like, is this model useful for anything? Well, clearly, it can solve cool problems like TC1 and whatnot. I said that there was a slight exception to the fact that TC1 is the best that we know, and that is that we now know that bipartite maximum matching can be solved in catalytic log space as well, which is kind of a nifty thing that we did not expect, I think. And it goes via a de-randomization of the isolation lemma, which is also quite nice. It's a de-randomization in a sort of cheating sense. Again, we'll talk about it later. But this definitely was not something that we had expected to get before about a month and a half ago or something like that. So. But this is still talking about catalytic. What can it actually do in the non-catalytic world? And there are 2 lines of work, one of which I know very little about, and one of which I know quite a bit about. De-randomization of BPL. So this has been a problem that's been attacked from all angles over, well, many, many years. But in particular, it's seen a big revival in the last maybe 5-6 years. William Hosa improved the results of Sachs and Joe not too long ago by a square root log factor, but it's progress. And people have been coming up with better, like de-randomizing from weaker assumptions, or stronger de-randomization, where if you assume weak, de-randomize log space into order log n bits, you can de-randomize it with like an extremely small constant stretch and all that. And this is related to questions like targeted PRGs or certified de-randomization and these kind of nice win-win arguments. And it turns out that in recent memory, a lot of them have used techniques from catalytic space. In particular, techniques related to de-randomization, which I've mentioned a couple times, and which will be one of the 2 techniques that we talk about. So the kind of hallmark result that has happened as of recent is either, and this is kind of in an instance-wise fashion, so I'm lying a little bit, either BPL is in NL, or NL is in, can be done with polynomial time and log squared space. So we know that NL is in log squared space by Savage's theorem. This is a very not polytime procedure. This uses exponential in log squared n time. Meanwhile, for polytime algorithms, the best that we know is very slightly sublinear space, like 2 to the log n minus square root log n or something like that. It's very, very small savings. And this is saying you can get all the way down to the best space usage that we know while maintaining polynomial time. And if that doesn't hold, then you can de-randomize BPL using non-determinism. So the techniques involved in this is not a purely catalytic technique, but the techniques are pulling from the catalytic literature. And the second one is, well, we already saw it, tree evaluation problem. So as I mentioned before, tree evaluation problem is now very close to not becoming a counterexample, or provably not becoming a counterexample for log space versus polynomial time. Maybe you think this log log n over log 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 n factor is inherent. That's fine. I don't. But what do you get from it? Well, you get an amazing recent result of Ryan Williams, which I have to mention, which is that Turing machines which use time t can be simulated by Turing machines which only use space square root t log t. So this is a quadratic improvement over what was known from 1975, and it's the kind of quadratic improvement that no one I've ever talked to believed was possible. A corollary of this is that space n is not in time n squared, or roughly n squared, which makes also the first direct progress we've had on P versus P space in a very long time. And this technique is literally just plugging in tree evaluation somewhere. I mean, it's a very direct use of what's going on in the catalytic world. So this is, I think, the most bombastic result that we've had in the field, bar none. And yeah, I think it asks nice questions about how far you can push this technique. Can you do this with catalytic space? Can you improve this thing to t to the epsilon if I allow you some poly t space? All of these kinds of questions are up in the air. So if you want to talk to me about this or other questions that are open, ideas, I would love to talk about it. But for now, let's actually say why catalytic space helps. So I've told you that it helps. I've told you you can do kinds of wild things with it, but any questions? All right, time for the audience interaction portion of this. Okay, some of you know the answer to this question already, but do something with catalytic space. Just, what would you do? I've now told you that this thing helps. If I give you a log space machine and I give you a polynomial amount of memory that you have no control over, do something with it. And if you already know how this works, then don't do something with it. But I'm always curious, does anyone have any intuition about why this could be useful? Okay, try something even if you don't think it works.
Okay, sure.
Sure.
If you can have many states in your, some extra states in your machine, then you can make some kind of counter on the tape, which
Ooh, tricky.
maybe isn't.
So I guess if we think of the machine as being constant size in the typical setting, then you can even think that the log space work tape has all the external information on it. So
maybe you could try and find a pattern on the given tape, save it somewhere smaller, and then use that as your memory and then restore it.
okay, yeah. So if you can find a pattern on your catalytic tape, then there's kind of something that we all know how to do and we all love, and that's just compressing, right? That's maybe not exactly what you were thinking of. Funny enough, what you were thinking of is how we get this robustness result that I have in the middle here, this lossy result. But yeah, if your catalytic tape has patterns on it that you can exploit, then there's possibly a compression argument to be had. And if you can compress a significant number of bits off the catalytic tape, then that's free memory. So what happens if there are no patterns on the catalytic tape?
Use it as like a random string.
Very good. Compressor random. The very descriptive name of the first technique. That was actually, apparently this wasn't the first technique discovered. It went unpublished for a while, but I thought that they found this argument first and then later found the other one we'll talk about. Turns out it was all around the same time. It's neither here nor there. So to illustrate how compressor random works, I'm going to talk at a high level about one of the most recent results. Technically, it's much more involved than I'm talking about. No. Technically, it's slightly more involved than what I'm talking about. But in essence, this is where this has all the information. So I said matching is in catalytic log space. How does it work? Well, matching, maybe one of the most classical algorithms that's known for matching is the randomized NC2 algorithm for it. And this is based on the isolation lemma. So to do matching in randomized NC, it's enough to just take the determinant of the matrix of the adjacency matrix of the graph that you're given. And again, we're thinking of bipartite matching. If you did this with no if you take the determinant, you in some sense get a sum over all of the matchings, but with plus and minus signs. And so you get some cancellations. How do you get around these cancellations? You assign each edge a random weight. And the isolation lemma, this is Momole Vazirani, says that random weights implies only one min weight matching. Maximum matching. You can think of this as perfect matching. We end up getting maximum matching, but think of it as perfect matching for the moment. So if you take the determinant, if there are no matchings, you're going to get 0 for the determinant. You want to avoid getting 0 other times as well. And the way you do it is you assign these random weights. It will isolate something of minimum weight. And then it turns out that this thing will then be encoded in the low order bit. And since it can't be canceled out by any of the larger weight ones, the determinant will be non-zero. And that's how the whole argument works, roughly speaking. So what are we going to do in catalytic log space? Well, I know how to compute the determinant. I already told you that TC1 is in catalytic log space, which means determinants are A-OK by me. And where are my weights going to come from? Just take them from the catalytic tape. Block up your catalytic tape into a whole bunch of chunks and use it as your random weight assignment. Now just take the determinant, and a couple of things could happen. It could be 0 or it could be not. And well, if it was 0, it's for, again, one of two reasons. Either there is no matching, or your weight assignment was bad. And we just have to deal with the case where your weight assignment is bad. But what is a bad weight assignment? Bad weight assignment says that there's two matchings, M1, M2 of min weight. Pick some edge that's in M1, but not in M2. All right, what is the weight of this edge? It's the weight of M1 without it. Oh, sorry, it's the weight of M2 minus the weight of M1 without it, right? If you can find the matching M1 without this edge, and you can find the matching M2, you know the weight of this edge under my weight assignment, right? They're both the same min weight assignment. So delete the weight of edge E. Just look on your catalytic tape, find this edge that's in one of the matchings and not the other, delete it. I just told you how to recover it, right? Just find the matchings again. And then you can find the matchings without incurring the, without needing to know what the weight of E is. You just need to know one matching has it and one matching doesn't. They're the min weight ones, so you just look for the minimum weight of any matching. And then you can free up log n bits on your catalytic tape this way. And if you repeat this procedure a whole bunch of times, eventually you either are left with a weight assignment that's good enough to solve your problem, or you freed up a polynomial number of free bits on your catalytic tape, and then you just run the polytime algorithm. You have so much free memory, you can do whatever you want. So you run a polytime algorithm for matching, and then you invert everything in the way that I just described. Now, there's technical details, obviously, but they're surprisingly not that difficult. This is the moral structure behind the argument. So in essence, it comes down to, can you devise a situation where if your catalytic tape is random enough, you win? And on the flip side, if it's not random enough, you can detect this fact and do the compression argument that is implied by the fact that it's not a random tape. That's the whole game, and it comes up in a lot of settings to get a lot of very nice algorithms, including the de-randomization of randomized catalytic log space. Goes by this as well. So that's technique 1, and that's the more intuitive one. I'm not going to force you to come up with technique 2 because it's weird. So the second technique is just kind of nonsense. This is what the tree evaluation and all other kinds of, all the early techniques rely upon. And it essentially comes via adding things and then subtracting them later. Sounds easy. What do I mean by this? So in tree evaluation, remember, I was thinking of nodes which take 2 children as input and spit out one output. So how would you typically evaluate a node like this? Well, you would start by computing the left node somehow. You'd then compute the right node. Shift this down. So you compute the left node, you compute the right node. You use these 2 values to compute the value v, and then you erase your left and right nodes. This is just like how anyone would think to use space to compute these. But as we discussed before, in that intermediate phase, where you're remembering this L here, in order to compute the R, you're going to need more space, and that's going to tank you. So let me switch and think of this as arithmetic for a moment. So now think of all these values as numbers with some number of bits, and think of each block of memory as just storing a number. So to recap what I said before, but in slightly different language, you would first find a way to add the value L to your left-hand node. Then you would use that to, and then you would add the value R to your right-hand node. You would put these 2 pieces of information together to add the value V to a 3rd block of memory. And then erasing, let's use a different language. Let's just say I subtract L and I subtract R. So this is pretty much all what I said before, but in arithmetic language. And the trick of these algorithms is that you can do this even when this memory is completely full. So I'm giving you the ability to add the value L to some block of memory while leaving the rest of it untouched. And I give you the ability to do the same with R. And furthermore, I give you the ability to subtract them back out. Using this, they devise a view of V as some kind of polynomial in L and R. And through this and some cancellations, derive the ability to add V without ever directly looking at L or R. So V is going to end up taking in as inputs either just this base value, say tau L, or the composite value tau L plus the value at L. And from evaluations of the polynomial on these points, they can determine the value of the polynomial at only L and R. And that's kind of where the arithmetic magic comes in. It's really cool. It's really beautiful, based in classical techniques like Barrington's theorem or the follow-up work by Benor and Cleve. And it exploits one of the few strongly non-monotone things we know how to do. Like in arithmetic, you can subtract.
And that's this thing we were using is reversible computation?
Yeah, so all spaces, classical space is reversible. This is a known fact.
I'm talking about subtraction. How do I abstractly understand such?
Oh, subtraction. Oh, but if you think of these as arithmetic, like numbers, then subtraction is just the flip side of addition. So for example, let's take the leaf values, right? Let's say L and R are actually just inputs at the bottom of the tree evaluation instance. Then it's clear why I can add or subtract L or R, right? If I just think of these things in the interior as numbers. Think of everything as being over a field, for example.
Mm-hmm.
So, everything is mod P. If I want to add L, that's easy. If I want to subtract L, also easy, so I just look at it. But now let's say this value V was the sum of L and R. How do I add the sum of L and R? Well, I add L and I add R. How do I add? How do I subtract the sum of L and R? Well, I subtract L and I subtract R. Right? So like the trick then becomes handling operations like multiplication and whatnot, or more complicated operations, whole polynomials. But in the arithmetic world, addition and subtraction are basically, they're not that different. And that's something that we rely on. So notice here that the whole reason I moved to saying that the way of resetting, of erasing L and R was just subtracting, is exactly so that the net result of adding L and subtracting L is the original memory that you had. You can't just erase the value in there once you're done with L, because this memory tau L might be of use to you. And why did I didn't even say, why am I doing this kind of crazy procedure? It's because imagine at the moment that I've added L, now I need to add R. Before, I had to allocate a whole new block of memory and do the operations there. Now, it's no different, right? This value in the interior here is now tau L plus L. But if I want to add R here, I still have 3 blocks of memory to work with, right? You don't have to allocate a whole new block of memory to pull into this procedure. You just use the same 3 blocks of memory and rotate off which one is the left child, which one's the right child, and which one's the target. That's the whole point of this procedure. These values in the interior are going to end up being the composite values of a ton of different partial information throughout the tree. It's like instead of pebbling this tree using only H many pebbles, you pebble it using like, I don't know, 15 pebbles per node. It just so happens you store all the pebbles in the same block of memory. So it's a very kind of weird algorithm, but it works. So this is arithmetic nonsense. And again, in the second half of the talk, when we get to the technical portions, I'm happy to talk about either the compression argument or the arithmetic argument through a framing. There are problems that we can frame using it. But for now, since I only have 4 minutes, open problems. CL versus P. It's the big one. I've been working on this for 8 years. I've made no progress. So if you have any ideas, please come talk to me. Applications, more applications. We've got time versus space. We've got tree evaluation problem. We have de-randomization of BPL. What else? These things are begging to be used as subroutines and for the techniques to find more applications in other space-bounded areas. So any sorts of questions outside of the catalytic world that these techniques can be useful as subroutines or just inspiration for would be an amazing thing. More techniques. I've outlined 2 techniques. There are 2 techniques. Like there's pretty much nothing except for the 2 that I outlined. There's a lot of different ways of doing them, but these are the only 2 things we know how to do so far. So even improving these techniques by bringing in harder tools from like arithmetic and whatnot. As I was mentioning to some people before, this arithmetic magic, the latest incarnations end up being like error correcting code machinery in disguise. And we didn't realize it until way after the fact. Is there more tools that we can bring in from fields like cryptography and whatnot to aid us? Are there better compression tools? All the compression arguments that we have right now are basically elementary. They're clever, but they're elementary. So finding new machinery to use would be an amazing thing. Could probably come up with like 20 more open problems, but this is really where things stand right now. So I'm going to say that's it for the first half.
The win-win argument you talked about,
Mm-hmm.
can you say a bit more about it for
This BPL and NL or right. So essentially, you kind of you make up a computation of BPL. And so you have a computation of BPL by NL, a proposed computation, and because it's NL, it's oh wait, no, let's go the other way around. Yeah, let's go the other way around. So let's say that the computation of NL can be structured as a sort of like like whatever poly n steps of log squared n memory. Is that the right way to think about it? It's something like this. So take the computation of the NL machine. And roughly speaking, it's either correct or it's not. Like either NL is an SC2 or not. And if it is, like if the computation is correct, then you're done. If not, then you use its failure as like a, you're essentially going to use the computation itself as a pseudo-random generator for BPL, which I don't exactly know how to describe it, but essentially it comes down to like, if your machine fails, then it is you can exploit that as a source of randomness and then just like completely pivot into the BPL versus NL thing. So it's an instance by instance thing, as in you get a graph and either you can estimate the random walks probability using non-determinism, or you can do it in SC2. One of your two algorithms will work. You don't know which one. And so you just kind of cook up the situation in which it would work in one. And if it fails, then you use that as a PRG against the other. They're very kind of strange arguments. But one maybe higher level one would be like you go about doing the you say you wanted to come up with a low space algorithm for I don't know, BPL or something, like a log space algorithm. So you like go chugging along for a while, and once you filled up a bunch of bits, you ask, is this enough? Like, do I have a good enough source of randomness to from the computation thus far to just output randomness and then solve BPL directly? And if it is a good enough source of randomness, then you just like stop whatever computation you were doing and just do BPL. But if it's not, then that means it's not very random, and so you can compress it. So you just shave off a bit, and then you kind of continue as you were going on. So you're constantly compressing more space so you stay within some space bound. And as soon as you fail, it's because you actually have something that's random enough to work. Like this isn't going to work directly, but intuitively, these are the kinds of arguments that we're talking about for win-wins. And of course, they use like reconstructive PRGs and other annoying stuff. All right. And we're back to the second half of the great catalytic relay. So I asked people a little bit during the break about what they want to hear about, the arithmetic part versus the compression part. And I think it's going to ultimately be a little bit easier to push on the arithmetic part for starters, and then we might get back to the compression part in a little bit. In fact, I've already sort of given one of the key components, like a lot of the key components for the arithmetic argument in this last little discussion that I outlined. So let me do it one more time. So the input-output behavior we're going to think of is we're going to think of all the objects in a tree evaluation instance, since this is the easiest one to outline, as being numbers over some field. And our main subroutine is going to say that given three locations, which are already filled in with some internal values, assuming the ability to add or subtract a value L wherever I want, add or subtract a value R wherever I want, I can from these derive a way to add or subtract a value V to wherever I want. And this kind of behavior, it was not implicit in Barrington's theorem, but you can see Barrington's theorem in this way very clearly from the follow-up work, which is by Benor and Cleve, who showed that tree evaluation is in log space when all of your functions are plus or times. So think of, again, like your log n bits as corresponding to numbers over some finite field, and all of the internal functions either are just the sum of the two numbers in the field or the product of the two numbers in the field. So it's a very restricted instance where the functions are not at all these crazy difficult ones, and yet it seems like the same pebbling logic should, roughly speaking, occur. And they show that that's not true by using this kind of behavior, and we'll just prove the whole thing now because it kind of displays how this arithmetic stuff works. So again, I'm going to assume exists programs PL and PR, and PL, let's say, is that RL plus plus is equal to the value L. My notation's getting sloppy, that's all right. R plus is equal to the value R, and from it we want to derive a program PV, which is RV plus is equal to V. And again, I'm going to allow the inverse programs, which subtract the value. So you have access to both the plus or the subtraction. And we're going to derive these programs from the ground up. Again, the functions we have to work against are plus and times, or rather plus, times, and the leaves. So let's just do the leaves first. So leaf value xj. How do you add or subtract a leaf value from memory? Yeah, you add or subtract a leaf value from memory. It's sitting right in front of you. Just look at it, add or subtract it. I'm not even going to bother writing it down. Now, V equals L plus R. Okay, usually this is the warm-up stuff, but I actually already said both of these programs in the right before the break. So what do? You just run the PL program and then the PR program. Okay, as I've stated it here, you're adding L to the left child and R to the right child, but you can shift things around, so you're adding to whatever blocks of memory you want. So if you want to add the sum, just like add the left child to the place you want, and then add the right child to the place you want. And now you have the sum of the two values in the place you want. Nothing to it. So the difficult part is times. And I need space, so I'm just going to erase this. So L times R. If you are allowed to add L and you're allowed to add R, how do you add the product of the two? This is obviously the challenging part of it. And once you see this, it's kind of clear how these arithmetic stuff works. So if I tell you this is possible, you can basically go back and like try a bunch of things and eventually figure it out. I'm just going to do it the most direct way I know how. How do you get the product of L and R? I mean, there's only one way to start, right? You run the PL program and the PR program. And at this point, your register, I'll keep track of my register memory on the right-hand side. So they start off as tau L, tau R, and tau V. And so this adds the value L, this adds the value R, and then I'm just going to add their product. Right? I have to get the product somehow, so let's just do it. So if I take the product of RL and RR and I add it to my third register RV, you get, this one's going to get annoying, so how much space do I have? There we go. You get all the cross terms. Right? This is just take the product of these two values up here. Now, what do we want? We want this one, and we want this one, and we don't want the rest. So, how are you going to get rid of the rest?
Subtract it.
Yeah, good. Do PL inverse, which thus removes L from the right-hand register, and then subtract the product. So this is minus tau L tau R and minus tau L times R. Great. You probably see where this is going. So next I'm going to reverse which one is in the register and which one isn't. So I'll put L back in here, and I'll remove R, and then I'll subtract again. And this gets rid of the L tau R term, and also has an extra minus tau L tau R. And for the grand finale, you reset your last register, so you run PL inverse. Notice at this point that my other two registers are exactly left the way that they started, as I was expecting. And you add the product to get a plus tau L tau R. Thus getting these two to cancel out, and being left with exactly tau V, the original memory, plus the product of the two. So this is what I mean by arithmetic magic. It's like utilizing the fact that you have cancellations and you know how your memory is operating. So the salient parts about this is that your register memory, the memory that you actually use to do computation, is only 3 numbers. So it's 3 log n bits. And there's a second salient part of this, which is the runtime. So how long does it take to run this procedure? Well, I have a circuit of depth log n. At each node, I make 1, 2, 3, 4, 5, 6 accesses to the level below it. You can reduce this down to 4 by reorganizing things, but let's just say you make 6 accesses to the level below. So at the top node, you're going to have to compute the left and right child 6 times total. Each of those is going to access the level below it 6 times total, and so on and so forth. Easy recursive argument says that the total runtime of this is going to be roughly 6 to the power of the height of the tree. Height of the tree is log n. This is a polynomial runtime, and thus you need an extra log n bits to keep track of how long you've been running. Plus maybe order log n bits to actually perform the field operations like plus and times and whatnot, and to know which instruction you're running at any given time. But the ultimate thing is that the runtime memory is log n, and the actual memory for holding the values from the tree is log n. And that gives you a log space algorithm.
How is this related to the catalytic model you introduced?
Right, so these techniques technically predated catalytic, but the first catalytic paper showed a very similar result for circuits with majority gates. So CKLS 14. Assuming you have a program PX, which says that some registers Rn, I'll put it up here, Rn plus is equal to a vector X. From it, you can derive a program P majority, which says that R out plus is equal to the majority of X.
Is that on the catalytic tape?
Yes. So this is the move to catalytic is because when you're computing the majority gates, you have n inputs coming in. So in the thing that I just outlined, you only have 1 number on the left and 1 number on the right. There's only log n bits, right? So it's fair to think of all of this as being in free space. But suddenly when I have a majority circuit, even just to store all of the values of the level below, if I'm trying to bypass pebbling and I'm doing everything as a polynomial, I'm gonna have to store all of the values below me in memory. And I can't do that into my free space, right? So my register memory is gonna be some poly n size thing. So how am I gonna possibly deal with that? Well, it's fine, because my register memory is this memory up here where I don't care what's already written in it. I can always undo it later. So that's why I made the distinction between the memory that it takes to keep track of your runtime and the memory that it takes to write down values. Because what we're going to show is that you can do a polynomial runtime procedure to compute a majority circuit in the same way as what I just outlined. However, all of the actual memory for storing your values is going to be in the catalytic tape. It has to be, because you don't have enough free space to do it otherwise.
So, but I guess asking the same question, I think the point with this thing that you were just adding and subtracting from is that that means that you can do all of these computations over on the catalytic space, on the catalytic tape. And essentially, if you just store, I guess, what the value was in the cell for the sink, like you copy from the catalytic space whatever is written in the sink position, so you save it, and then you run your algorithm, and then you can just sort of copy from the catalytic space tape and subtract, and now you know what the value is, and you sort of use only a constant number of bits, I guess, over on the actual tape, plus your bookkeeping, which is logarithmic.
Exactly. Yes, that is going to be how this algorithm works. Yeah, so I can spell this out more carefully if anyone needs this. Notice that we're now, in the previous one, I assumed I had programs to access the left and right child. I can't do that here. I can't access each of the bits individually, because if I did, I'd be making n accesses to the level below me. And then my runtime would be something like n to the height, which is like n to the log n, which means just to do the bookkeeping, I would need log squared n memory, and this is trivial. So we're going to move to a different model where I can access the entire level below me, and from it access the entire level above me. So in fact, what they actually show is that if you have a whole bunch of majority gates, which are all accessing, so this is like layer, whatever, this is layer L and this is layer L plus 1 of the circuit, that if you can add all the values at layer L plus 1 to your catalytic memory, then there's a different, then using it, there's a program that adds all the outputs at layer L into memory. But for now, I'm just going to show you how to do one gate. It parallelizes quite nicely. And again, to stress, all of this is going to be happening in the catalytic memory. Your free memory is exclusively for bookkeeping, like how long you've been running, which operation you're trying to execute at the current time, and for getting the final output, for storing the final output value. And since we're allowed a polynomial amount of catalytic space, we're not going to be so strict about how we use our register memory anymore. It's enough to use the register memory, up to like a polynomial blowup. The thing we need to keep track of is that you only access the level below a constant number of times. Because we still have a log depth circuit, which means I can't go accessing the input to this majority gate like poly n times. A constant number of times is the only amount that I'm allowed. Good. So the way that this works is by an arithmetic characterization of the majority function. All right, let me do this step by step. So we're going to test, this is actually going to work for any symmetric function, but I'll just spell it out. So you want to test if the number of ones in your bit string x is at least n over 2. So for each possible, this should be k. Sorry, k. So for each possible value, which is a 1 of the function, you're going to test if it has exactly that many ones. How are you going to do it? So fix some k. You're going to take the sum of the xi's and subtract off k. This value is 0 if you got the right value of k, and it's going to be something else otherwise. Now, using Fermat's little theorem, if you power this to the p minus 1 and you take a mod p, you're going to have 0 if you got the right guess of k and 1 otherwise. We're going to flip that around, so do 1 minus that. So now it's going to be 1 if you got the right guess and 0 otherwise. And now summing over all possible correct guesses of k, if any of one of them is the correct number of ones, then you're done. You're going to get 1, and otherwise you're going to get 0. Is that clear? Great. Okay, so what do we need to do? We need to be able to compute unbounded sums, and we need to be able to compute powers. So I'm going to fix the field p, of course, sorry, p greater than n, right? Yeah, you don't want to wrap around by accident. So p is going to be bigger than the number of inputs. But again, we're okay with dealing with polyns, so this is not a big issue. All right, so remember, I gave you access to px, which adds each of the bits of x to a separate part in memory. How do you get the unbounded sum from it? So first I want p sum, which is our sum plus is equal to the sum over all I of xi. So how do we do this? Roughly speaking, yeah. Now it's like you have to target the x's are all going to go into their own registers, so you have to do a little bit more footwork to it. But basically, you just do r sum minus is equal to the sum of all the ri's. Then you run the program px, and then you do r sum plus is equal to the sum of the ri's. Right? You subtract off the value that was originally there, and then you add back in those values plus the sum of the xi's. That's really all it is. Sorry, RIN. Yeah, those are the input registers. Is everyone okay with this program? Okay, because we're not going to get far otherwise.
So we need to store the sum of the Ri.
Yeah, so this is the first program. This allows you to compute this interior thing right here. I mean, of course, you can subtract k off at some point as well. So this gives you this thing in the interior. And from this, that's going to be like the first building block, and this only accesses the program px once. I guess to reset it, it accesses it twice. So fine, px inverse, just to make sure you've reset. Okay, so that's two accesses. And now we're going to come up with a program for power. So I'm going to assume now I have a program PV, which just says RV plus is equal to the value V. And again, you should think of this as like V is the sum from the last step. And from it, I'm going to derive P raised V to the K, which says R out. It's going to be the output register, so it doesn't matter. Plus is equal to V to the K. So I will give you the ability to compute a value. Now you have to show me how to compute the kth power of that value. And remember, I only want a constant number of accesses.
And typical cases, K is large.
K can be as big as N, yes.
So for constant, you already did something.
For constant, yeah, you can just take the program for multiplication and cheat your way through it. But unbounded fan-in multiplication does not follow from anything that we've seen so far. In fact, it ends up being quite annoying.
It's not doable still, right?
Well, it's not doable optimally. I can do it in n recursive calls.
Oh.
Product, I can do in n recursive calls. You can actually, for one product, you might be able to get it, but ultimately, yeah, high degree stuff is hard. But it turns out powering is not hard.
Repeated squaring?
Repeated squaring is still going to take you, like if k is super constant, that will still take you a super constant number of times. Logarithmically less, but that's not good enough. So the trick is you're going to look at the value vk in terms of, and this is something that we do all over these kinds of arithmetic techniques. You're going to switch the basis in some sense to being the part which is just involves taus and the part which just involves tau plus v, because you have access to one or the other at any given time. Plus v minus tau to the k, and this is equal to the sum of k choose I times minus tau to the I and tau plus v to the k minus I. Yeah, good. So again, the trick the trick here is that we always have sorry, I should label these tau v. These are tau v. There we go. Right. So how is this actually useful to us? Well, if I run the program PV, so now RV equals tau v plus v. Then I'm going to use some auxiliary registers, Ri. I'm going to say Ri plus is equal to Rv to the I for all I equals 0 up to k. So Ri equals tau I plus tau v plus v to the I. Now I'm going to do PV inverse, getting rid of this, and then I'll do my output register. Plus is equal to the sum of k choose I minus RV to the I times R k minus I. Okay. And the net result of this is that R out is equal to tau out plus, I'm switching the outs, that's all right. Sum of I equals 0 up to k of k choose I times minus tau v to the I times tau v plus v to the k minus I plus sum k choose I of minus tau v to the I times the actual value tau I, right? In this product, in this product here, this part has two terms, this and this. And this part is exactly what we wanted. This whole sum is exactly the thing that we're ultimately shooting for, but we also get this junk term down here. However, it's not that impressive.
How can you compute this complicated sum?
What do you mean? It's just a sum of k terms. I mean, like these all have log n bits. You just go term by term. I loop over all I. I just I just use my log n free memory to actually compute this value. It's all mod p, and p is some poly n bit value. So as long as I'm just computing field operations based on what's written in front of me, there's no issues. Is that all right? Cool. And now, I mean, it's not too interesting to see exactly what happens. You just like repeat this procedure again with a minus sign to reset your RI registers. And then you do this instruction again. So this is with a minus, and this is with a minus. So at the end, once you've reset the tau i's back in, you do the same thing here with a minus sign. And what does it do? It subtracts out some k choose I times, now it's tau minus tau v to the I times, now this rk minus I is just tau k minus I. Oh, sorry, this was supposed to be k minus I. There we go. And these two cancel out and you just get what you want. Yeah, so it's all arithmetic magic. I should note here, this only works commutatively. If you can make this work non-commutatively, I think I can show CL contains NC2 and actually some more powerful things. So we're not, just non-commutatively as in matrices. Yeah, just think of everything that, what?
Even 2 × 2 matrices.
I want larger matrices, but the actual mechanics of like operating on them, I don't care about. That part, I know how to basically do matrix multiplication and everything in catalytic log space. I'm not worried about the bare bones operations of this procedure. However, it does still hold that this main equality, this main trick that I have up here doesn't carry over. So like, I'm up Schitt's Creek so far. Good. And the last thing I'll say here, I have some pre-recorded talks on YouTube and whatnot that you can find, which is telling about how tree evaluation goes. And what's tree evaluation? It says if you have px, which again is like rn plus is equal to the vector x, then from it you can derive a program pq, which is rq plus is equal to the polynomial q over the inputs x. Oh, notice here, by the way, I only made 4 recursive calls once again. PV, PV inverse, PV, PV inverse. Constant number of recursive calls, and then those are you're using those to access P sum, which makes 2 recursive calls, so you make 8 recursive calls in total. So we show how to do this for arbitrary polynomials, including non-commutative ones. The recursive calls is going to be order the degree of the polynomial q. So it's no longer a constant. However, in tree evaluation world, where you're getting log n bits from the left and log n bits from the right, if you treat this thing as a polynomial, it only has degree 2 log n, which means that the total runtime of my whole thing is 2 log n to the height of the instance, which is log n, which means the space that I need to keep track of it is log n log log n. And that's exactly where our space usage comes from. Space usage comes from. Our register memory is optimal, as with all the other ones. So that's the entirety of our approach. And again, there's some tricky stuff going on here, but it's nothing earth-shattering. This is like a basic equation from finite fields or roots of unity. So yeah. Any questions on arithmetic?
For your result to work, you said just interpret everything as operations of the polynomials, but now you're not just powering, right? You need like large products.
For sure. Yeah. You need to be able to handle an exponential number of monomials, each of which can be a product of all of the input variables. So it is not at all immediate how to get this thing to work. You can get it to work. Degree of the polynomial, again, if you think of it as the number of variables multiplied together, getting one monomial with this many recursive calls roughly, that's not too hard. You can figure it out. getting it to work for exponentially many in parallel, the obvious adaptation of the first product I showed you gets you 2 to the number of 2 to the degree, regardless of the number of monomials, which is quite nice, but it's not enough. That was our first tree evaluation paper. That's how we got log squared n over log n. You do some balancing of the degree and the representation. In order to get it down to linear, you just need to think of some nice tricks. If you know Reed-Muller codes, you can actually figure it out from that. And if you know any better codes, again, please talk to me. Yeah.
Do you expect to be able to do this non-commutative in constant with constant
Number of recursive calls? I have no intuition. I hope so. I don't see a barrier to it. Not off the top of my head, at least. There is possible that there is some barrier. But yeah. And again, I only need it for powering, right? I don't need it for arbitrary non-commutative functions. I should say, by the way, if you get this number of recursive calls for this last statement that I just said down to a constant, tree evaluation is in log space. It's just an immediate consequence. So that's the whole barrier right now.
Something about the space, extra space going down to log now. So what
yeah, so you don't improve the register programs I've been talking about. You instead basically, you don't even rebalance the tree. You just play with the fan-in of each node. So again, you're going to pay linearly in the degree, which means if you merge layers to blow up the fan-in, your degree blows up in tandem, but it doesn't blow up, but the height also decreases. Now the height decreases only by a log factor of the blow up in the fan-in, but since the register memory is only log n and the time memory is log n times log n, you can balance these two, and the balancing point is a log savings. That's just the number of layers you merge together.
So it's more like play with the structure of the tree and then
Correct.
apply your algorithm.
Correct. So this improving this register program I've written up here, there's a soft barrier to it, which is that this is like the number of times you have to evaluate a polynomial to interpolate. Like it's degree plus 1 many evaluations that we end up doing, which is the number of recursive calls we end up doing. And I don't know how, you have to change your view of things to beat that, because you certainly can't interpolate with less than d plus 1 points. So it will take a totally different view of register programs to bypass that barrier. However, if what you're doing is external to this, if you take this as the best register program, but mess with other aspects of the tree, like, pebble some nodes, decrease the height, do whatever, that's all fair game. So it would be nice to improve this to an optimal, to a constant number, but I don't know that that's necessarily possible. However, even ruling that out, you're not screwed for tree evaluation, even using this general framework. These are the only arithmetic functions that I know how to do off the top of my head, but it's only because these are the only ones that have been studied off the top of my head. If you have a favorite arithmetic function, feel free to attack it with this. There's some surprising things that come out. Or converting things to sums of power. Sums of powers of sums is something that we did in a recent paper, and it gets you a little bit in some corner of something. All right, good. So now let me say a few words about compression. And to do this, I'll talk about another small result that I didn't mention earlier, a nice little robustness result. So let's call CLP the polytime restricted version of catalytic log space. This is catalytic log space where I force you to run in polynomial time no matter what your catalytic tape is. Now this thing is clearly in catalytic log space because it is just a CL algorithm. It is also in polynomial time because you have to run in polytime no matter what your starting catalytic tape is, including the all zeros catalytic tape, right? So a polytime algorithm can just initialize, just pretend it's the catalytic algorithm, and it will run in polynomial time. And a result that we showed last year was that actually these are equal. So this polytime catalytic log space exactly characterizes the problems you can solve in both. It's a small result, but the nice thing about it is it sort of inaugurated the entire line of compression techniques that we have going on, and it's a very kind of sneaky technique. So for this, you need to know something that I mentioned offhandedly earlier, which is that space-bounded machines are reversible. As a result, due to Lange, McKenzie, and Tapp from 2000, it works in the catalytic space world as well. What do I mean by reversible? I mean, if you start with a machine M, you can convert it into machines M forward and M backwards, whose space usage is almost exactly the same as the original machine. So like off by like a plus or minus little, or sorry, big O of 1 many bits of memory. That has the same behavior as the machine M in terms of the same input-output behavior. And if machine M transitions from state A to state B to state C, then M backwards transitions from state C to state B to state A. In other words, like, it doesn't have to be 3. The point is just that the operation of M backwards is exactly the reverse of the operation of M forwards. This is a transformation you can do to space-bounded machines. It does not necessarily preserve the time of M. That's a very important point. But this is going to be a necessary step in our discussion.
Statement exactly? If the original machine runs in space S and time t?
Forget time t. If it runs in space S, the time, you get no guarantees on time. But if it runs in space S, the new machines M forward and M rev run in space S plus O of 1. It's like S plus 3 or something.
And so this guarantee is like, whatever, does this apply only to states which M could reach? Or is like,
No, so
I just drop any state on M, and if it would take the following M steps going forward,
yep,
then M forward would do this, and M reversed would.
Yes, it will reach states that the original M didn't reach. In fact, the way it basically works is you take M, you know, whatever its state space was, and maybe it had some unreachable states like this. You just do an Eulerian tour around it. That's how the reversibility works. Because essentially to go backwards, you just take the tour backwards. So at you have to add some extra information that says basically like which edge you're looking at in the radius, and you know, whether you're going into an edge or coming out of one, like little information like that. Again, this is a fairly classical result, and it just so happens to work for catalytic machines.
Doesn't it just say that there was a permutation branching program that sort of captures the computation of the machine?
I think you have to be careful about that. Maybe that's fine. For our purposes, it's much cleaner to think of it as a reversible machine. It might not be I guess if it's reversible, it should be a permutation. Okay, so maybe this does follow. Yeah, you might be correct.
It's a state.
A state, like a configuration in the machine. So think of it as whatever's written on my log space work tape plus the state itself within the DFA that's coding up the machine's brains, plus the identity of the tape heads, just all the information about a configuration of the machine.
So by machine, we really mean the input is fixed as part of the machine?
Oh, sorry, this is right. This is saying that once I fix X, the machine M backwards acts the reverse of M forwards. But the transformation from M to M forwards and M backwards is, you know, that's just a generic transformation.
So the claim is that from a machine M, you can create this pair of machines that satisfy these properties, and that for any given X,
it does the same thing as MX, like it outputs the same value, 0, 1.
Okay.
Yeah. Good. All right, so that's going to be one tool. The second tool we're going to use is, I told you earlier that CL is in ZPP. Let's prove it. To do this, Let's prove that L is in P first. Why is L in P? This is the 11th hour audience participation thing, just in case anyone's asleep. L, exactly. So again, we consider every possible configuration of the machine. There's only polynomially many of these things. And if you ever repeat a configuration in your computation, the configuration has all the information. So if you repeat it once, you're going to repeat it ad infinitum. This can't happen, which means you can visit each one at most once, at most a polynomial member. Cool. So for catalytic log space, you can't, the number of configurations is exponential, right? It is 2 to the size of the small machine workspace times 2 to the size of the catalytic tape times some poly n for all the exterior things. So this won't work. It won't work directly. However, one nice thing that you can say is that if you look at any 2 starting states of the machine, any 2 starting states being any 2 distinct catalytic initializations of the catalytic tape, you fix the x and you run the machine forward, I claim that they can never actually run into each other. And the reason why is because, again, a configuration has all the information, which means if they merged into each other, they would end somewhere. And that thing would, it would have a catalytic tape written down at the end, and it's going to be one or the other at best. It's not going to be both. So for a fixed x, 2 computation paths can never intersect. Which means that the number of configurations is 2 to the s times 2 to the c times poly, whatever. S is the small tape, c is the large tape. But the average number of configurations that you will reach, so like the total number of configurations you can reach between all of the lines defined by x is this many, which means if I pick a random starting one, you're averaging over 2 to the c many possible starting states. And so the average length is just polynomial in n. It's 2 to the s times poly n. Right? Like your state spaces can divide it up into these chunks. There's 2 to the c of them, and the total size is 2 to the c times poly n. So what's your ZPP machine? Pick a random starting catalytic tape, run the machine for 2 to the s times poly n times a bigger poly n. If it halts, you have the right answer. If it doesn't halt, just say I have no idea. It doesn't halt with probability extraordinarily low. So that's it. So great, there's the 5-second argument. Now, we're going to put these 2 things together to get the algorithm that I said earlier. CLP equals CL intersect P. And the idea is a random catalytic tape only takes polynomial time. I just proved that to you. Can we compress any catalytic tape that takes too long? If I can do that, then I'm good to go. I compress my tape if it's taking too long, and then I just start over again, pulling in some more catalytic bits. If it runs in polynomial time, I'm done. Otherwise, I can compress again, or I compress again, again, and eventually I end up with a polynomial amount of free space. What do I run? I assumed this thing was also in polynomial time. I just run the polytime algorithm for it in the freed up space, and then I do the decompression. Does that make sense to everyone? So again, we can expect this to work because a random catalytic tape will run in polynomial time. Any CL machine is already a CLP machine most of the time. So what we're going to do is detect the few times that it's taking too long and find a way to do a compression argument. And if you can do a compression argument, then again, the fact that you're assuming you have both a CL machine and a polytime machine means at the very end of the algorithm, instead of running your CL machine, you just run the polytime machine in your freed up space. And note that then you've compressed a polynomial number of times. Each compression argument took poly time because we just ran it until it went for too long. And in the end, you run a polytime procedure. So the whole thing is in polynomial time. Thus, it is a catalytic log space algorithm that runs in polynomial time. And that's the whole argument, except for the compression piece. How do you compress a catalytic tape that is taking too long? So imagine I have a starting state tau. This is just the initial state of my machine. And I'm going to run it forward for some I steps. As I said, one of two things is going to happen here. Either you finish, I steps was enough to run the whole machine, you halt, you output the correct answer. Then you're done, right? Think of I as some polynomial in n. Or two, you don't. And so you end up at some intermediate state where the catalytic tape is, let's say, tau sub I, and you have the rest of your configuration, so your work tape and all the other nonsense, is some V sub I. Right. Now, this machine is reversible. I assume that this was the forward machine that I was talking about, which means if I ran this backwards for I steps, I would reach the state tau, the starting state tau. We're going to assume that the start states are distinguished. Say they have all zeros on the configuration portion, right? They have some tau in the catalytic part, and then everything else is zeros. That is going to be what I define as a start state, right? Which means if I see a start state, I can recognize it. Which means if I ran backwards from tau I vi, and I kept a counter of how long I was running, after like when I reach a start state, I know that that was A, the start state that I started in, and B had the number I. Remember, you can't hit any other start states in this reversing procedure because all of the start states have disjoint graphs. Good. Now, the trick is that this means that tau comma I can be encoded as the pair tau I vi, right? I can recover tau comma I from tau I vi by just running backwards until I reach a start state. And so if the number of bits in I is strictly greater than the number of bits in vi, then this is a compression procedure. In particular, if I started with my machine, so my machine M originally operated on this catalytic tape tau, that's where my original CL machine, which is not polytime bounded, is running on. I just extend the catalytic tape by a little bit, and I have it write down the number I for me. It can give me any number that it wants, because it's not going to matter. I'm going to run for that many steps, and if I halt, then I'm done. And if I don't, I replace tau comma I on the catalytic tape with tau I comma vi. Because the number of binary bits to write down this number I is more than the entire configuration, this is good. And why does this make any sense? Because since the size of I is greater than the size of vi, the averaging argument tells us that almost every catalytic tape will only run in less than I steps, right? I is a number that's that's a number up to 2 to the something, and that 2 to the something is bigger than what the averaging argument above gave me for the whole rest of the configuration. Which means for a random choice of I and tau, you will halt in time. This is the whole procedure. So you just run this poly many times until you can brute force your thing. This we just informally dubbed time step compression, and we have juiced this thing for all of its worth. So for example, if you want to show CNL is equal to CL, CBPL equals CL, even CPL, which is unbounded randomness CL, can be reduced to CL. All you do is just discover the entire configuration graph that you're working with from your starting state tau. And if it's too large, you compress with the argument I just said. And if it's not too large, then it's basically just a BPL or an NL computation in disguise as a CBPL or CNL argument. It's a poly-size graph, and I want to run connectivity or randomness on it. So the formal statement that we show is C whatever space with basically anything you fill in, S comma C, reduces basically in C space S comma C to a blank space S algorithm. So there's a catalytic space procedure which incurs no losses, which transforms the instance or solves the problem directly into an instance of the regular version, and then we just appeal to the fact that NL's in CL, BPL's in CL, PL is in CL, etc. So basically, this just becomes C space, and this also becomes C space. Put these two together, you get a C space algorithm, and that's the whole procedure. The only thing I have to tell you is how to actually discover the graph. This you just do by essentially the same Eulerian Tor argument that I talked about. You have to do it in reverse for technical reasons. It's not that interesting. The paper is like, I don't know, 10 pages or something. And the proof is 2. So that's my plug, I suppose. These sorts of arguments, again, have now been seeing interesting play in the world of just de-randomizing BPL in different settings, these kinds of compression-based arguments. And we originally came up with it as an information theoretic argument, and only Ted realized that it was a compression argument a while later. Ted or Jiazi Li, who was also on the paper. But I feel like there can be harder compression arguments that work here. This is like a very blunt attack on the thing. So harder tools, again, more techniques would be a lovely thing to have. But at a high level, these kinds of compression techniques are perfect for catalytic space, where you have all the space you need as long as you can make something of it. So I guess that's enough for the technical portion, and I'm happy to explain any results in more detail, anyone who's curious, specifics, ideas, etc. Thanks. Any more questions?
Can you go back to the argument you showed? I guess this one. Okay, tau is, I assume tau is the initial catalytic tape.
Initial catalytic tape, yep.
And where does is I written?
Yeah, so your original machine only had a catalytic tape of this length, C, whatever it was, that had tau written down on it. We are now simulating this by a new catalytic machine, which we want to run in polynomial time.
Which has longer.
Slightly longer, right. We're going to extend it by this many bits for a time step I. And in fact, since we need to compress many times, we're going to extend it by like polynomially many i's.
Okay, so you have a new machine whose catalytic tape length is polynomially larger.
Right.
Additive polynomial.
Additive polynomial. And in fact, really, you can just, since you're compressing 1 bit off of this thing, you can just have each of these be the 1 extra bit to fill in behind it. So yeah, it's going to be like if your original machine was like S comma C, S free space, C catalytic space, then you're going to transform it into one that has roughly S free bits, and then it's like C plus S times whatever the poly n, the runtime of the C machine. Or of the P machine, sorry.
Solving this problem.
Yeah. The runtime or the space usage of solving the problem kind of naively.
Okay.
Yeah. I should say, because of this argument that I just outlined here at the end, this compression argument, like the total space usage, again, it's S comma C here. There's no losses. This one, it depends on what your loss is in your simulation. So for BPL, for example, as I mentioned earlier, BPL is in free space log n, catalytic space log squared n, which means this C blank space log n, or like S comma C, ends up being in, let me just say it. So CBP space S comma C is in C space S, it's order S, C plus S squared. So the overhead is really, really small for most values of C. And it exactly matches up with if you just decrease C as much as you can, you like don't get any better than the best de-randomization, but you get everything up to the best de-randomization. For NL and PL, it's not so good because you just have to do determinants and whatnot. So in those cases, you will get like S comma C is in S comma 2 to the order S plus C, which means that these ones only work for stuff like CL, where the catalytic space is exponential in the free space. The BP space algorithm works even when the parameters are mismatched. In our first argument, that wasn't true, but now it is.
And when you write these parameters, you always omitting multiplicative big O?
Yeah, but most of the multiplicative big O's are not bad. Some of them might be, like the big O here is probably like 2, maybe 3. This C has no no, this is like 1 plus little o of 1. This thing, I don't know. I have no clue. It's like Nissan's PRG, but with a bunch of extra gas behind it. So And then once you get to this part, like, oh, well, whatever, the thing that was formerly there, then I really have no control over the constants. But they aren't as like, you don't need to do SD connectivity. You don't need to do like Rheingold or anything. They're not truly atrocious. Most of the constants that appear in these things are like, yeah, 2, 3, etc. Except for the runtimes. The runtimes are like end of the 9 or stuff like that. So. Yeah. Oh yeah, my favorite catalytic open problem. Find any practical implementation of anything that I've described here. Like these runtimes are so bad. Even balancing, right? Like don't get optimal space savings. Get a little bit of space savings, but keep the runtimes under control. Do I don't know, SD connectivity in slightly sublinear space while keeping the time quasi-linear or something like that, using our techniques. Those kinds of things are all open and a nice frontier.
Okay. Well, thanks again.